intervals and hypothesis testing for categorical data. That's why we're dealing with the proportions is what we're dealing with. So when given a statistics problem, we use a one sample confidence interval for proportions when they are asking us to estimate the percentage or proportion of the population. Once we know which inference procedure to use, we check to make sure we can meet the conditions. So again, as we go forward, any process that we're doing, we have to make sure we meet the conditions before we actually do the calculations. So is it random? Is it independent? Is it normal? Those are the conditions we're referencing to. Again, when we're thinking about with proportions, we need looking for this simple random sample. We're looking for the randomized experiment in the process of them talking about it. For independence, we're doing the independent rule, the 10%. And then for the normal, we're doing the n times p greater than or equal to 10 is what we're doing in that aspect. So the shape, at normal conditions, sample size is large enough that n times p hat is greater than or equal to 10. And n times 1 minus p hat is greater than or equal to 10. So as we're doing these, again, we may not know what P is, the population proportion. So we're using the sample proportion to help us figure out, hey, do we meet the normal condition? Our center, our mean, is going to be basically, when we look at it, it's going to be mu P hat. So that's just going to be equal to whatever P hat is. And let's see, the spread. So in order to calculate the standard deviation of P hat is equal to the square root of P hat times 1 minus P hat over N, as long as we meet that 10% for independence. So again, is 10 times little n less than or equal to big N? As long as we meet that condition, then we can do the standard deviation. Since we don't know P, with large samples, P hat will be close enough to P, so we can replace all the P's. I went ahead and replaced a lot of those P's with P hats, just so it doesn't confuse you, to check the normal condition. Now, how do we create the confidence interval? Again, this is on your the study guide or the formula guide for the AP test. So your statistics, so in our case, it'd be P hat plus or minus the critical value, which is our Z star. We're going to find our Z score that's associated with it, basically. We're going to work on finding that today. And then the standard deviation, which is also known as the standard error. Okay, so that's that square root part. What is the standard error? We use, this should be a hat here. We use P hat for P in the standard deviation formula since we don't know P, so which it is called the standard error. The standard error is what's after the Z star. And again, we use this to help us in the confidence interval for the standard deviation. Now, what is critical value Z? Or Z star, okay? Because we see it in the formula as a Z with an asterisk on there. Again, we pronounce that like Z star is what is sometimes what it is pronounced as. So Z star is like our Z score from back in our normal curve. So we get a critical value from the normal curve. So if we want a confidence interval of a 95% level, we use 2, since 95% of the data is within 2 standard deviations. Now that's basically using the empirical rule. Okay, that's saying that when we're looking at without a calculator, if this generic statement here. If I'm doing a 95% confidence interval, then that means that as I look at a normal curve, 95% of my data is on the inside, which means there's 2.5% and 2.5% on the outsides. And if we think back to when we did the normal distribution with the empirical rule, that was the cutoff for -2 deviation and +2 deviation is what 95% was between. So this little saying it's generically just 2 is basically using the empirical rule. As we look at table A and we start looking at using the calculator, that 2 is actually going to be a decimal. Okay, it's going to be a decimal smaller than 2, just a little bit. Okay, anyway, so when we're doing calculations on confidence intervals, we're using either table A's value or the calculator value for the z-star. We just don't use the generic 2. Okay, just to keep in mind, those are something we had in the notes there, just to think about 95% is in the middle. There's roughly, hey, that's 2 standard deviations away from the mean in both cases. So they asked us to use table A to find the critical value for Z. So again, here's where I'm going to draw a curve. I got my 95%, so 95% in the middle. And again, there's 2.5% on each side. Now, I'm trying to figure out the critical value associated with a 95% confidence interval. So what we're technically supposed to do is I'm actually trying to find everything. This would be the positive Z value. And then this number over here would be the negative Z value. That one over there. Whenever we're doing critical values for confidence intervals, hypothesis testing, it's always positive. So we're always using the one on the right is what we're doing when we're doing these confidence intervals and so forth. So, so with that in mind, if I'm on this Z right here, if I'm at this Z star on the right-hand side, technically how much of the area is to my left? How much area is over here to the left of it? 97.5, right? So with that in mind, I want to figure out what is the Z star associated with an area of 0.975 to the left. So when we're doing table A, I don't go to where, I go to 0.95 in the middle as I go back to my table A, which I think I have in my handouts. And I go to table A. And 0.975 would be on the positive side. And as I zoom in, and 0.975, there we go, 0.975. So I was lucky that actually being one of the ones. So that is a 1.9, and it's in the 6th column. So I know that the Mr. Stevens. Wrong button. I know that the Z star, as I go back to my notes here, I know that the Z star on the table A, that's associated with the 95% confidence interval. So a Z star for a 95% confidence interval is actually 1.96. Again, when I look at the next one, what is a Z star for an 80% confidence interval? Again, thinking about a picture, we draw the picture. We got 80% in the middle. That means there's 10% on each side. So when I look for this, I need to remember I'm going from the right side, the positive Z, and I'm actually looking for 0.900 on the inside of that table. So we go back to table A, and then we go for 0.900, so 0.9. All right, here we go. We're stuck with this. 0.900 is between those two numbers. Which one is it closer to? Is it closer to the 08 column or the 09 column? Yeah, I'd say the 08. So with that in mind, we're going to use a 1.28. 1.28 is what we're going to use for our Z star here. Man, I forgot that again. My apologies. All right, so that's going to be a 1.28. Now, here is what I would say. They will have that answer version with a confidence interval using table A. They'll have that answer with grade by. Okay, I will have that on our test to grade by if you choose to use A. Okay, use the table A. Most people probably go to the next thing I show you, how to get those things with the calculator. Okay. Anybody remember how to find the Z-score associated with an area to the left on the calculator? What feature we need to use? We use inverse norm. That's what we use. So again, you can do it in your head, but we're basically trying to find this number right here. So that's the 95 plus the extra little piece here. So that's actually we're trying to use the area is 0.975. It's the Z, so what's my mean and my standard deviation? 0 and 1. So now I can go split screen. Give me a calculator. Clear it out. Second, VARS, inverse norm option 3. And then my area is 0.975. My mean is 0. My standard deviation 1. I'm doing what's to the left, so I hit enter. And then get down to the bottom, paste. And then I get, notice how more accurate it becomes, 1.95996. Which technically, if we ran it to the fourth decimal, what do we get? We get 1.96, right? All right. Now, how many are using the same version of calculator I have on the screen? All right. Now, if you noticed, Alex, I noticed you're not. Okay, so you will have to do what I just did every time. Okay. If I go back to doing that inverse norm, just to show you, the newer software actually, gives me an option that, I can actually say, you know what? I can just say a 95% confidence interval, and I want to do the center. And then I hit enter, I go down and hit paste, and now that tells me that it's from negative 1.959 to positive 1.959, blah, blah. So we just use the one on the right side. So if you're using an older software of the calculator, you're going to have to do like what I did with the picture and put the number in the middle, what's on the outsides, add the middle number with the extra part on the left, and then do your inverse norm. Okay? If we have the newer version of the software, then I can use whatever percentage they tell me, just stick it in there and do the center option. Okay, so there's some benefits either way. We get the same answer. Okay, when we do the center option, we're just worried about the positive one. We don't worry about the negative one. Okay, we don't have to worry about that. Now, the other way you can go about doing this, if you want, is we know these two Z stars are the same number, they're just opposite signs. So what you technically could do, once you start this process and you get your area to the left, you can technically do an inverse norm and have your area be 0.025 and then 0 and 1, and that would give us the same answer. It would just be negative, we just dropped the negative. So you could just do what's on the left side of the interval, not inverse t, and just say 0.025 and then go left, and that gives me my negative, and then I just drop it and I say, okay, we're using 1.95996 in my formula. Okay, so you can do that way as well. just remember you're dropping the negative. All right, so if you don't want to draw the whole thing, more or less what you're doing is you're taking 1 minus your confidence interval, 1 minus 0.95 is 0.05, splitting that answer in two because they're on both sides of the thing. And then I just use the 0.025 and do the left of it and just drop the negative. So there's always ways to do it, it just depends on which makes sense to you. Now I will say this. With this chapter and the next chapter, typically when we look at confidence intervals that they're asking us to do on the AP test, it's either a 90%, 95%, and a 99% confidence interval. Sometimes they squeak in a 98. They never ask us for a 71% confidence interval. They never ask us for like an 84% confidence interval. Okay? Now they may on the homework assignment ask you to do one of those crazy percentages. So if you're goofy like me and memorize useless information, I typically memorize when I see the 95% confidence interval, I automatically write down 1.96. Okay, when we do a 99, I memorize what that decimal is and I write that one down. Okay, and I just memorize the ones that I need and that's all I use. Okay, or if you don't want to bother yourself with useless information, do you guys have a copy of the formula sheet stuff? Did I send that to you? Okay. So if you find that for me, find that sheet on. I don't know if I put where I put it for you guys. I know we got table A on Friday and next week. We get to do hypothesis testing. Okay. And so now this is where this is what we do. This is actually what's after spring break. This is when we're dealing with means. We got to do what's called a T-star. This one sheet right here, here's our confidence intervals, and then this is basically the Z-star at this last row. So as we look at what confidence interval am I using, and I erase all my chicken scratch there, all my circles, notice how what they have above the 95% confidence interval is 1.96. Okay? And so, again, I don't mind wasting my brain cells and memorizing several common decimals that they use. Those are the three most common ones they use on the AP test, those Z-stars. And so I just kind of just memorize them, and that way I have it. Okay. But again, to save time, on that on the paper sheet, you just get to that one table and grab all your Z-stars you need right from that bottom row. Okay, which saves some calculator typing in sometimes. Okay, or if you forgot to add the extra piece on the side to lose the middle one. Okay, so just to give you some options, whichever ones you want to do. All right, let's get back to our heart of our notes. All right, so sneaking back in here, 99% confidence interval. Again, we're doing an inverse norm. Technically, 0.995 is what's to the left. That's the area. Because, again, it's 99 in the middle. Then we split up a 1% to the outside edges. So our area is 0.995. Mean is 0. Standard deviation is 1. Remember, when we do a free response, we got to indicate how we got that number. Okay, so either write down table A and you memorize the number, or you type in this code for the inverse norm. You should get something here like 2.575 is like 829. Is that what it says? Okay. So, all right. Next part. Scooching down. Using this information, our new formula for constructing a confidence interval for the population proportion P is as follows. P hat. Let's get a different color. Let's go green. P hat plus or minus, again, our Z star times the square root of P hat times 1 minus P hat over N. This formula can only be used when the normal condition is met. And therefore, that means that we went through this process checking the greater than or equal to 10. Are we okay? We can only use that formula if we meet that condition. That's the main thing. If we fail one of the other conditions, we still can't use it. We stop. Especially with proportions, because there's no other options. With means, we have some other options. If you're smaller than 30 and this occurs, then we can still do it. So once we have calculated the confidence interval, we interpret it. So our 4-step process, again, in the beginning of the state phase, what proportion do we estimate and at what confidence level? We're going to give you an example here of how that started. We want to name the procedure that we're using. We are using a 1-sample Z interval for proportions. We need to specify for proportions. We just can't say 1-sample Z interval, because we can have a Z interval for means. So you're going to have to specify, are we doing proportions or means? Okay, right now we're only doing proportions, so it makes sense. Once I do, after spring break, the means unit, now we got to, so we got to make sure we specify. We got to show all of our conditions, random, normal, independence. In the do stage, we say if conditions are met, we get to, perform the calculations, and then we get to compute what p hat is. So you're going to show what p hat is, then indicate how you got your Z star. And again, they had 1 minus the confidence level divided by 2, because that's like 1 minus the C level divided by 2. And that's where we were doing. And this one is set up to where it's using that just the left-hand portion is what that's set up for doing. It's using like that negative 2.5 or the 2.5 area. And then we get to go through and compute it. In our interpretation, here's the phrasing we learned yesterday. We are blank % confident that the interval from blah, blah, blah captured the true proportion of what is the context of our problem. All right, so we're going to actually go through and do several of them for the rest of the class. Most of the rest of the class is doing examples of confidence intervals. So on this first part here, it says Mrs. Smith's class looks at a simple random sample of 102 pennies from a jar of more than 2,000 pennies. They want to estimate the true proportion P of pennies more than 10 years old in the collection with 99% confidence. Sweet. Their sample had 57 pennies that were more than 10 years old in a collection of, and 45 pennies that did not. Okay, great. We will estimate the true proportion of pennies in the jar that are more than 10 years old with 99% confidence. So there's our statement phase. We will estimate the true proportion of pennies in the jar that are more than 10 years old with 99% confidence. Our plan is to do a 1-sample. A 1-sample Z interval. We have to say interval. And then 4 proportions. And the reason why we got to say interval is because when you see the word test, that means we're doing a hypothesis test. So we need to make sure that we're specifying, is it an interval or is it a test that we're doing? All right, is it random? All right, let's see. As we look at our conditions, I see an SRS of 102 pennies is what they set up here in the problem. Woohoo, so I met the random clause. Normal. Our P hat was 57 out of 100. All right, so is 102. Is 102, our sample size, times 57 over 102, is it greater than or equal to 10? Well, yeah, the 102s cancel and 57 is greater than or equal to 10. And then I checked the other part. They did tell us that we're not. They said 47. So our 1 minus P hat would be the 47 out of 102. And as I checked that one, we would say is 102 times 47 over 102, greater than or equal to 10. And we would say, yes, 47 is greater than or equal to 10. So we met the normal condition. Now we get to go on to independence. So 10 times n. So 10 times 102 gives us 1,020. How many pennies were in the jar? $2,000 pennies. So, hey, that's less than it. That's less than what our population is, so we met that condition. Okay? Now, what are we going to do? We're going to do, says we did, conditions are met. So our one sample Z interval for proportions. Again, we have the p hat, 57 over 100, or 102, sorry. So as I look at my formula of p hat plus or minus z star times the square root of p hat times 1 minus p hat over n, we got 57 over 102 plus or minus. Now you can turn that into a decimal. Just use all the decimals. Okay, you can turn that into a decimal. 57 plus or minus. Now my z star. What type of confidence interval were we doing? We're doing a 99% confidence interval. So my z star would be basically doing a inverse norm of my area would be 1 minus 0.99 divided by 2. That would be my area. Now, you can find that off on the side if you want. What is 1 minus, sorry, that's not a minus sign. What is 1 minus 0.99 divided by 2? So that would be, isn't that like 0.05? 0.005. 0.005 is what that is. 1%, half of 1% would be, yeah. So my area technically is 0.005. My mean is 0. My standard deviation is 1. And so let's go to the inverse norm. Shoot. I hate it when I do that. Inverse norm and 0.005, 0 and 1 to the left. Again, if you want to do the center option, you can. There's multiple ways. So that tells me my decimal is 2.5758. So my, again, I like going on the Z star out 4 decimals. That way I know I'm accurate. Sorry, I lost my place here. So my Z star here, my Z star for a 99% is 2.5758. So that would be 2.5758 now times the big square root part. And I'm running out of room. All right, so I'm going to recopy that down. P hat, 57 over 102, times 45 over 102, over 102. Now it's a matter of us going through the calculations. So I would not type that. We can't type in a plus or minus symbol in the calculator, so we got to simplify this part over here. Remember, that whole part over there is the margin of error, because sometimes they ask us for what the margin of error is. So as I split the screen, And I say, all right, what is alpha y equals, what is, oh, I really don't want to divide, so I'm going to make the fractions. What is 57 over 102 times another fraction, 45 over 102, and all that is over 102. I hit enter. I'm then going to square root that answer. And then I'm going to multiply it by 2.5758. And so my margin of error, so I have 57 over 102 plus or minus 0.126635. So now I need to say, okay, what is 57 divided by 102? That is 55.88235. So now I need to basically add and subtract the 0.126635 from it. So I'm going to take that answer and add the answer up above. And that tells me that on the right side, because when I add, that tells me the right number. The right number is 0.6855. And then when I go back and say, all right, give me that number, and then subtract that square root part, and then enter, and that gives me 0.4322. So there is my confidence interval. Now I will show you an easier way to do this with the calculator. The challenge. Sometimes on our multiple choice, all we have to do is have the correct setup. And so we got to make sure we can show the correct setup of the formulas at different stages as we're doing things. So now we're ready for the interpretation. So I'm going to, okay, hold on a second. 0.4322 to 6855. 0.6855. So I'm just copying that up so I can zoom in and write. So as I go to write it, we are 99% confident the interval from 0.4322 to TO 0.6855 captures the true proportion of pennies in the jar that are more than 10 years of age. 10 years of age. And there's my final statement. Okay. We just can't just write the confidence interval. We just can't write the numbers and stop. We've got to interpret it in the conclusion. Okay. So we're 95% confident that the true proportion of pennies that, in that jar that are 10 years of age or over is somewhere between 43% to 68% or 69%. Okay? It's roughly between 43 and 69% of the pennies are greater than that age, or that, that are more than 10 years of age or older. Now, that's the first one. Any questions before we get into the second one? Because now it's just a matter of just repeating and doing little things. Any questions? It's a lot. It's a lot by hand. We're going to do one more by hand, and the rest of them we're going to do in the calculator. Mackenzie, question?
This is more of a question, I think, for Unit 7, honestly, but
Sure.
I remember, when we got this kind of data, we wouldn't, set a proportion like it was different. My thoughts are a little jumbled right now.
You're fine. I don't blame you. It's a lot of stuff in 2 weeks. It is.
Like,
It is.
Prior, either if you got a proportion, it'd already tell you like 0.9 or something like that.
Right.
Or you would get like data like this where it wasn't a proportion, but we made this into a proportion.
Right.
So is that something we can also do for unit 7? Like that kind of work, or is it just like a confidence interval thing?
Just a confidence interval. It's just, in Unit 7, when we were doing some of the proportion work, we were given the population proportion.
Mm-hmm.
All right, so we knew what P was, whereas now we don't really know what P is.
Okay.
And so that's why we're using a P hat, a sample proportion, to kind of estimate what proportion is the true population. We think it's somewhere where 95, in this case, 99% confidence. It's between, there's either 43% of those 2,000 pennies are 10 years and older, or it's less than 68%. That's what we're 99% confidence that the actual percentage is somewhere between these two values, is what we're saying. Okay. Now, we could find out what the true one is let's put all 9,000 or 2,000 pennies on the ground and start separating. Okay. Great little Friday night activity or snow day activity. Okay. So in this case, and as we do things, we don't know the true population parameter. All right, here in this case, the true proportion. After spring break, it'll be the true mean, the mu, the population mu.
So it's just different because you're solving for something
Yes.
stuff.
Yeah. So, and again, then we're not calculating a probability. It's just saying, hey, we're confident we're between these two values is where the true thing is going to fall, is between these two things. Now, that's a pretty broad range. Remember, yesterday we talked about the bigger the confidence level, there's some sacrifice. Okay? The bigger the confidence level, the wider the range. So if I want that percentage, because we're going from 43% to 68%, that's got a 25% range. Okay? If I want a smaller percentage range, if I want my width to be smaller, what do I need to do? That goes back to yesterday's lesson. If I want to decrease that wideness, that margin of error, to make my interval to be smaller, what can I do? There's two options. I can change the confidence level. How do I change it? I got to go down. Okay, I got to decrease my confidence level. That makes me if I decrease the confidence percentage, that makes me a narrower width. Okay, the margin of error gets smaller. Okay, so the width is not as. The other thing we talked about was the sample size. Changing our sample size. Instead of doing 102 pennies, we got to change it, make it smaller, make it bigger. In this case, it'd be make it bigger. Because we want to divide by a bigger number inside the square root number, so that way there's a smaller number that's being added and subtracted. We want a smaller number that's being added and subtracted, so that means I need n to be bigger. Okay, so it's lower. If I want a narrower range, confidence interval range, then I want to either change the confidence level, make it smaller, or I need to divide by a bigger sample size. So I need to change my sample, from 102 maybe to 150. But I can't go above what? How many pennies are in the jar? How many pennies are in that jar? So that's how much the sample was. There's 2,000 pennies. So if I need to still make sure I meet the independence clause, I can't be bigger than what kind of a sample? What's 10% of 2,000? 200. So if I want to try to get a narrower interval, get them closer together, instead of being spread apart by 25%, get them closer, then my sample size needs to increase, but I can't go above 200. Because 200 times 10 is 2,000. I can be equal to the population, I just can't be bigger than it. So my cap of doing sample sizes has got to stop at 200. I can't do 250. I can't do 300. Because then I fail the independence clause, and therefore I can't do it. Okay, so okay. Those are some of the sidebar questions that we get asked on stuff. All right, let's keep on going. Again, you can always work ahead of me. Try to stay tuned with me. Sorry if I'm boring you to, sleep. All right, next one here. Alcohol abuse has been described by college presidents as the number one problem on campus and an important cause of death in young college adults. How common is it? A survey of 10,904 randomly selected U.S. college students collected information on drinking behavior and alcohol-related problems. The researchers defined frequent binge drinking as having 5 or more drinks in a row, 3 or more times in the past 2 weeks. According to this definition, 2,486 students were classified as frequent binge drinkers. They want us to do a full confidence interval write-up, okay, the whole process. So as we do the statement phase, here's how we're going to craft it, okay? We will estimate the true, I skipped a word. The true proportion of college students now, was this survey done across the whole world? It was specific to what? The U.S. So we may want to say proportion of U.S. college students or college students in the U.S. We'd want to specify that because, again, outside of the United States, what's the drinking age typically? Well, it depends. Some of them 16, 18, depending on the country. Okay, so when you think about it, based on our drinking law of 21, I know some kids that are under 21 sneak drinks occasionally. Okay, but it is, some sarcasm in that statement there. But so we want to make sure we specify what type of college students is what we're saying this to. We will estimate the true proportion of college students in the United States that frequently binge drink with 95% confidence. Now, you could tweak that to be any way you want. Rephrase it. Don't get too wordy. Keep it at a nice, short, and sweet. Typically, when they write our problems here, sometimes certain sentences actually give us the whole statement phase. Real easy. We will use a one sample Z interval for proportion. And I usually like tying in here if conditions are met. I like putting that in the plan stage, okay? Because I'm getting ready to go through the conditions. I like to say, hey, I'm planning on doing this if conditions are met. And as opposed to later on where it had it like, hey, if conditions are met. I like to say in the do stage, conditions were met. So in the random, they tell us here 10,904 randomly selected there. So 10,904 randomly selected U.S. college kids, college students. All right, normal. All right, this is where we got to do the NP stuff. So 10,904 times 2486 over 10,904 is it greater than or equal to 10? Yes, 2486 greater than or equal to 10. And then we would go through and say, okay, 10,904 times something over 10,904. According to my notes, it's 8418. Sorry, 841. Yeah, 8418. And that's greater than or equal to 10. Yes, those cancel. 8,418 is greater than or equal to 10. So normal condition met. Independence. 10 times 10,904. That is 109,040. Reasonable to assume more than 109,040 U.S. college students. That's reasonable to say, right? Because what do we know some of the big major universities have as an enrollment? Like the Ohio State or like USC and UCLA. I think if you go online to see what the enrollment for college students at like the Ohio State, it'll probably say something in the 70,000s is what it'll probably say. And so, even UT Knox probably has somewhere around 40 to 50,000 enrolled. You know what I mean? So yeah, it's reasonable to say that there's more than 109,000. We can just pick a couple schools and we're already above that. Okay? Even the number one drinking school in the United States, a few years ago, was UT Knox and stuff. So I don't know if that's a good statistic to be to be associated with or not. So, but all right. So do the conditions are met. Conditions are met. So again, now we get to go ahead and do our p hat stuff. P hat plus or minus our z star times the square root of p hat times 1 minus p hat over n. So we know what our p hat is. Our p hat was 2486 over 10904 plus or minus what type of confidence interval? 95%. So for our z star, using table A, 1.96. That's how I would write it, because you know how I talked about before. I like memorizing useless information. Okay, so that's how I would indicate to the grader, okay, I'm doing this. Now, if you want to use the inverse norm, that's fine. You can use 4 decimals. The more decimals you use, like with inverse norm, it makes the confidence interval more exact. But again, they have both the answers down there. They have the answer for using 1.96, and they have the answer for using 1.9599. But they have both of those answers as confidence there to grade by. Okay, so you pick which you want to do. It would make sense to you. All right, so that 1.96 is going to go here, times the square root. Now the crazy fractions. 2486 over 10904. That is being multiplied by 8418 over 10904 over 10904. And this is the last one we're doing it by this way. Then I'm going to show you the faster way. Okay? So I'm going to get to my calculator and I am going to start doing the fraction part. So with that inside, clear the screen. Alpha, y equals, give me a fraction. Give me another fraction on top. And we got 2486 over 10904. And then times another fraction. 8418 over 10904. On the bottom, 10904. Hit enter. And then leave it like that. Second square root, second answer, enter. All right, that's a little bit better to work with. Now times it by our 1.96. There we go. All right, so I am now down to the plus or minus 0.0078746694. Now I just got to get the decimal for the first fraction. 2486 divided by 10904. Sweet, that's 0.22798978285. I'm going to let the calculator do my work. I always do the one on the right first. I like adding first. So I'm going to take my answer that I just had, and I'm going to add to it the 0.0. Oh, Mr. Stevens, you doofus butt. I'm going to go back up here and grab that decimal, save myself time. And that gives me 0.2358. 9. Round it. On the other one, we would say, all right, give me my 0.22, and then I'm going to subtract the 007, James Bond, and I get 0.2201. So there's my confidence interval. Now we're ready for the conclusion. We are 95% confident the interval from 0.2201 TO 0.2359 captures. Remember, captures or contains are the same thing. Captures the true proportion of U.S. college students who frequently binge drink. Binge drink. Bingo. Okay? So, I know as a teacher, like when we're writing stuff, we always say what we're writing so you can listen and you don't have to actually watch the screen and write down and do it like silence, and so forth. But I do feel it helps when I'm doing the confidence interval stuff to write that conclusion stage to actually say it out loud as I'm doing it over time. Because it just, for me, it helps burning in my memory how the phrasing needs to be. And then I'm just doing subtle tweaks. Change the confidence interval, the percentage amount, change the interval numbers. But just I try to keep that same format to try to help me memorize how I need to write. Because again, we have it now. We have hypothesis testing stuff that we got to add literature for interpreting. So to me, the more you practice it, hopefully it helps. All right. Now, how do we do it in the calculator? Woo! Because now we're done with doing it by hand. Calculator makes it so much easier. If I split my screen here, and I'll just go ahead and show you where it's in the calculator. Clear my screen. We're still going into stats. So we're going stats, going over to the test column. Now, anything that says the word test is a hypothesis test. Okay, that's what we're going to get into next week. So right now we need to focus on the intervals. So now, as we go down, do not use option 7. Option 7 is a Z interval for means. Okay, it's for means. We're not doing it. We're doing a Z interval for proportions. So we need to keep scrolling. And we need to go down to the next screen where it says 1 prop Z interval. A 1 proportion Z interval. That's basically their thing of saying a 1 sample. Okay? Now the 2 sample is what we get to do in the next lesson. Okay? When we're dealing with the difference between 2 things. So right now we're doing the 1 prop Z. So hit enter. Now we get to type in 2,486 out of 10,904. We're doing a 95% confidence interval. I hit, wow, look at that. And there's my interval. Same interval that took us like 5 minutes to get by hand. There is the interval right there. The p hat, notice the second number down. There's my p hat. If I did calculate it. I calculated it right here. There's my p hat. All right, so again, your choice. For the rest of the problem we're going to do this method. I'll show you how you need to write your script in the do stage. That will save us some time. Because anytime you're doing a formula like this by hand, it takes a while. Okay, but you do have that option to do it by hand, especially if your calculator dies in the middle of an AP test. Okay, if it dies, you got to do it by hand. So that's why we try to train both ways, with the hand, by hand, and also with calculator. Okay. All right. So, remember, this is what's on the AP test. This is the generic stuff they give you. They do give you some of the stuff here. All right, the standard deviation of the statistic, that's the stuff that's after the Z-star. So this stuff is what's right there after the Z-star. That's also known as your standard error. All right, ready to practice? Thank you for saying yes. So what are you going to do next year when you go off to college and your professor's not going to joke around with you and stuff? It's going to be like boring as heck and stuff. So, all right, here we go. According to an article in the San Gabriel Valley Tribune, most people are kissing the right way. That is, according to the study, the majority of couples tilt their heads to the right when they kiss. In the study, a researcher observed a random sample of 124 kissing couples in various public places, creepy, and found that 83 of the 124, or about 66.9% of the couples, tilted their head to the right. Construct and interpret a 95% confidence interval for the true proportion of all couples who tilt their heads to the right when kissing. Okay? So, those of you that have significant others, have you already started thinking about which way do you tilt your head and stuff on that matter? Do you tilt right or do you tilt left and stuff? Because if you tilt right, they have to tilt right. If you tilt left, they tilt left. Okay? Because if you go right, they go right. Or sorry, if you go right and they go left, then you hit noses and stuff. You right? You know what I mean? So, all right, here we go. We are in the statement stage. We're going to estimate the true proportion of couples that tilt their head to the right when kissing with, they said, 95% confidence. All right. Now, we didn't see it on the last two examples, but this is what I mentioned before. Notice the last sentence here. It says, construct and interpret a confidence interval for the proportion of couples that tilt their head to the right when kissing. Typically on a free response question on the AP exam, that last sentence will tell you how to start that first gate fix. Okay, it'll actually let you, it'll give it away, so you don't have to come up with the wording. Usually the last sentence will actually give it away that you just need to change construct to estimate, we are going to estimate. And then you can copy the rest of the stuff back down. So it makes it a little bit easier, instead of trying to come up with stuff, because again, I'm more mathematical, not English brain. And so having something like, hey, that's a trigger, I just need to use that, just change a word in the front, helps me out tremendously. Where our plan is to use a one, whoa, yellow does not work on a notes. A one prop Z interval. Now that is basically the coding in the calculator for P. And then we're going to check conditions. That's the same thing as saying if conditions are met. So random. They said random sample of 124. So a random sample of 124 couples. Normal. Again, you could get away with 83 is greater than or equal to 10. And then the other one would be, what is that, 41? 41 is greater than or equal to 10. Normal condition met. You can get away, since they're giving us actually physical numbers here. I know they gave us a percentage, but since they actually gave us the physical number, we can say 83 is greater than 10, and then what's the other part, okay? And then we don't always have to show the fraction. I know I've been showing the fraction this times that, but you can get away with still getting credit for that if you really show 83 is greater than 10, and then the other one, so forth, okay? Independent. 10 times 124. 1240. Here I would say reasonable to assume more than 1,240 couples. Again, nice short little thing. I know it's like a no duh, but again, which is short and sweet. We show it. Hey, it's reasonable to assume there's more than that many couples. You know, we please the graders in the process. Okay, and therefore we met independence. So now, we have met. So my Z star. Again, if you want to do inverse norm, my area is 0.025. That's what I'm going to use. I'm not going to use. You can use the 0.975 if you want. You know, if you want to. And then my mean is 0. My standard deviation is 1. And that gives me a negative 1.9599, which we know we're going to use just 1.9599. That's what we're going to use. Just the positive version. Now I'm ready for my calculator work. So now, technically, this is if you're doing it by hand. So now we would go through the whole process. Now they did give us p hat. Our p hat was 66.9%. So that's technically 0.669. So if I was doing it by hand, I could actually go through and say 0.669 plus or minus the 1.9599 times the square root of 0.669 times 0.331 over 124. So I could do that. Since they did convert the fraction 2 for me, and you can do the same thing if you convert it. But they didn't give me that percentage, so I could technically use that percentage and not use the extra decimals that are associated if I wanted to. Because I didn't do what 83 divided by 124 is. Is it a terminating decimal or is it a repeating decimal? Out of curiosity, what's 83 divided by 124? I'm thinking potentially repeating.
Yeah.
Is it repeating? Yeah. And stuff. So, just because 2 would be 62, 31. Trying to think if dividing by 31 always gives you a repeating decimal. So, now, how will we do it with the calculator? We're going to do a one prop. This is what we would say. One prop Z interval, INT. And then we would say X is equal to 83. N is equal to 124. And then my C level is 0.95. And that's what we could show for our work on the free response. That's what we'd have to write. And then now I can go over to my confidence interval and go over here. Cleared. And then do stat over to test. Go down to one prop Z int. Hit enter. Type in 83 out of 124. Still 95. Sweetness. Hit enter. And they tell me that my interval is 0.58655, comma, 0.75216. And then I'm ready for the write-up stage. We get to say that we are 95% confident, put the percent on there, 95% confident that the interval from 0.58655 to 0.75216 captures the true proportion. I need to adjust this Word document for next year, make it wider, of couples that tilt their head to the right when kissing. Again, the one prop Z int feature is a lot faster. It is a time saver. Okay, so I would highly recommend doing that from here on out. You don't have to. It's natural to do the opposite of what a teacher says. Because sometimes you do the opposite of what your parents want you to do. Yeah, it's just instilled into us. It's natural. All right. Last little bit. This is the last part right here. Rest of this page. Determining a minimum sample size. In planning a study, we may want to choose a sample size that allows us to estimate a population proportion within a certain margin of error. And again, if we think about a couple of, when we think about like the blast problem with the kissing couples, the confidence interval had a spread of about 17%, which means there is a margin of error about 8.5% is what the margin of error was. Sometimes we want to say, you know what, that's too big of a margin of error. I want a margin of error of maybe 2%, maybe 3%. Now, why would I want to do that? Well, maybe I'm in a manufacturing, company, and the machines are doing stuff, and I don't want a wide interval. I want a narrower interval, because that way I'm not wasting product, I'm not wasting stuff, and I'm trying to control costs. And so when we're looking at defective parts, we want to say, you know what? The defects, we want to have the margin of error be like something maybe 2% or 1%, because if we have too big of a margin of error and we let stuff out that's defective, what's that going to do to our reputation? Probably going to hurt our reputation, which means people aren't going to buy our product. And so there are certain situations when a smaller margin of error is needed. And so with that in mind, if we want a smaller, whatever the margin of error we want it to be, then we need to figure out, okay, what's the minimum sample size I need to gather in order to get to that margin of error size. Okay, so with this in mind, here's what we do. We can actually solve the right portion, basically what's after the plus or minus symbol is what that's telling us. Because remember, it's the point estimate plus or minus the margin of error. That is our confidence interval, our CI. So if I want the margin of error to be a certain amount, then I can figure out, okay, what do I want that sample size to be? So we're just figuring out, okay, what does this thing need to be, and so forth. I need it to equal a certain thing. So as we fill in some of this note part here, where p hat is a guessed value, when we're trying to figure this, they either tell us on a pilot study or past experience. So again, this is where they would say, the problem would basically say, hey, what's the minimum sample size I need to have a 5% margin of error? And they would say, based on a previous study, this is what the sample proportion was. Okay, so they're going to tell you that. Or if they don't tell us anything, like based on a past experience or a previous study, we use 0.5. We use 50%. Okay? So quick part of that there. Think about elections. Think about right now as there are different polls being out there about since Trump has been in office for roughly a month now, and are people in favor of what's going on? Yes, no. All right, when I go to poll somebody, you're going to answer yes or no. All right, man, sometimes they give you the category for maybe, but you know what? It's either a yes or no. Don't be wishy-washy. You're either in favor of what's going on or you're not. Okay? That's where when you look at situations and you're not sure what percent should I put in for the p hat for this minimum sample size. Is the situation basically a yes or no situation? If it's a yes or no situation, 50%. All right, we're just staying right down neutral in the middle is what we want to use. If they tell us there's a previous experience that was done or studied, then we use that sample percent, that sample p hat as our amount that we put in here. Okay, and we'll see some be both ways as we do stuff. All right, so here is our example. As I can try to draw all over the screen, and my thing timed out on me. Come on, why are you timing out on me? Don't be so stubborn. I'm almost done with class. Oh, come on, you little goofball. Oh, goodness gracious. Oh, yeah, it went black screen on me. That was like, Mr. Stevens, we hate you. All right, get it in there. Scroll to the back. Here we go. One problem. Here we go. So suppose that you want to estimate P, which is equal to the true proportion of students at your school that have a tattoo with 95% confidence and a margin of error. Here we go. Margin of error is 10%. So ME is equal to 0.10. So we know what's after the plus or minus sign needs to be equal to 0.10. That's what we want, no more than that. How many students should we survey to estimate P with a 10% within 10% within 95% confidence? All right, so great. So when we think about it, the formula margin of error is greater than or equal to our Z star times the square root of P hat times 1 minus P hat over N. Now, we don't know N. Did they say in here there was a sample or a thing already done? So in that case, our P hat has to be 0.5. You're either in favor or you're not. Or you either have a tattoo or you're not. Sorry. You either have a tattoo or you're not, or you don't. So my Z star, they do say that it's a 95% confidence interval. I know that's 1.96. Now, if I use the inverse norm and use 1.9599, I'm going to get a more accurate answer. It's going to be a little bit different, and I'll show you that. So, but I'm going to stay with this. 0.10 less than or equal to 1.96 times the square root of 0.5 times 0.5 over N. Now I need to do inverse operations in mathematics to solve for N. So the first thing I would do, I would divide both sides by 1.96. 0.1 divided by 1.96. I'm going to leave it like that. I'm going to do all my stuff at the end. That's equal to now the square root. 0.5 times 0.5 is 0.25. Again, I'm going to let the calculator do all the math at one time for me at the last stage. All right, now, how do we get rid of a square root? Yeah, so we square it. So that tells me I have 0.1 over 1.96 squared is equal to 0.25 over N. Now, I multiply by N, multiply by N. That gives me N times that crazy fraction squared. That's equal to 0.25. Now to get N by itself, or sorry, I put equal sign. It should be just that greater than or equal to. N, I would divide both sides by the fraction, basically. By the fraction squared is what I'm dividing both sides by. And that gives me that N has got to be greater than or equal to 0.25 divided by the fraction 0.1 over 1.96 squared. That's what I'm going to type into the calculator. That stage right there. So I'm going to go in there because I feel confident with my calculator skills. I'm going to go in and say, all right, what is alpha y equals on top, 0.25. On the bottom, I'm going to do parentheses. Alpha y equals, give me a fraction. 0.1 on the top. On the bottom is 1.96. Go to the side, close the parenthesis, and then square it. All right, that looks perfect to what's on my screen. I hit enter. N is got to be greater than or equal to 96.04. Now, can you have 0.04 of a person? No. So we're saying 97. I know 0.04 doesn't technically make a 6, make a 7. But in this world, we round up to the next whole thing. Because if we round down to 96, then we're not within that 10% margin of error. We're actually outside that 10% margin of error. So we're rounding up so we stay inside the margin of error that they're asking us to stay inside. Okay? Now, that formula is not on the sheet. It is partly sort of, but you got to make sure, and in the process, you just got to make sure you practice it. So, again, if you need me, let me know.